Yes, sir. Yeah. Now it's clear, sir.
है ना? So that is where we have two different timing definitions for D to Q and CK to Q. So are these timing? See, I'm spending quite a bit of time on these timing definitions because they are important. These are the kind of questions that will typically be asked in your interviews also. Okay. So once you go back, please reflect on these timing definitions. You will need to watch the video again, but it is important that you get sufficient clarity on it. If you have further questions, you can ask the TAs, ask me to me in the office hours, but get sufficient clarity on these aspects. Okay. Now we come to the timing parameters for the flip-flop. Do you see some change from earlier? What all has changed for the flip-flop versus latch timing diagram?
Sampling edge has changed, and also now D to Q is not there.
D to Q is not there. Okay. And
Sampling edge has changed.
sampling edge has
Setup
changed.
and hold, yeah.
Setup and hold kya?
We are defining setup and hold on the same edge. Like it can be defined in that also. Yeah, yeah. Okay. Yes, yes.
Setup and hold are always defined from the sampling edge only.
Yes, yes.
The key change is that now you do not have D to Q kind of timing, because flip-flop is not level transparent. It's not transparent at a level. It just samples at the clock edge. Okay. So very simple. We have this, instead of T pulse width, now we have a timing called T, which is cycle time or period. So T pulse width is no longer there. Other thing is that T DQ is no longer there. T pulse width is replaced by something called as T period, and TDQ is simply not there because changes in D will not be reflected. Anyways, they will not be reflected on Q. Are you able to see this? Any questions?
So in my previous question only, so the clock to Q. So for example, if I'm in here, for example, this case, the flip-flop, if I take the like transmission gate, that implementation in which I had transmission gate and the inverters kind of a low feedback. So sir, the path between, there's a path between the D2 like output. I mean, the input would flow from the D pin and ultimately they get finally latched to this Q pin. But exactly the clock to Q path, I cannot say that exactly there's a clock to Q path. I mean,
are you talking about the flip-flop or the latch?
Flip-flop, sir. Yeah.
Okay. So let's draw the flip-flop. What are we talking about? We have, what do you say? And in fact, we saw that, okay, there could be Q and Q bar that are driven like this. Hai remember
yes.
that?
Yes, sir.
So now you are saying that there is no path from clock to Q, but there is a path from D to Q.
So I mean that internally with the clock, this path is actually, I'm interested in how much delay, for example, if I do some changes in my inputs, and after how much delay there that input change will be reflected in my output. So
Yes.
effectively, I should be considering this D pin to and Q pin, right? The path between them, because clock inputs are not
CK is
getting
also
reflected.
an input, na? Clock is also an input, na?
Yes, sir, but that input, I get that, but that input is not getting reflected.
Why?
That is basically controlling.
So let us say clock was 0.
Yes, sir.
Let us say clock was 0. D could only come till here. It came here and it settled here. Now, input in D, change in D was not reflected on Q.
Yes.
So you cannot have a D to Q timing.
Okay. Okay. So
Whether
okay.
clock is 1, whether clock is 0, whatever it was, change in D will not be reflected on Q. Are you with me?
Yes, sir. Yes.
Huh? Now, let us say clock toggles. What happens now? When clock toggles, this tri-state also turns active,
Yes,
and
sir.
whatever was stable here is now starting to reflect on Q. So what has triggered this transition on Q? Is it change in D or is it change in CK?
It is a change in CK. Okay.
That is why the timing is defined from CK to Q.
Okay. 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 So okay. I mean, what exactly is the triggering edge, triggering signal that from where we calculate the delays? Okay.
Yes.
Okay, sir.
Okay. Devjit?
Yes, sir. Sir, does clock to queue delay depend on the amount of hold time that is there in the? I mean, suppose you have told me to reduce the clock to queue delay, and my hold time I'm not able to reduce. Then how do I frame it? Sir, can clock to queue delay be less than hold time? That's what I mean.
It depends how your data path, how long your data path is, and so on. So it depends. Yes, it can be done like that. That hold time is really very, very large. So okay, let us look at why we need a hold time. In this case, for the data pin, when we want to talk about setup time or hold time, we say that at the falling edge of the clock, this transmission gate becomes transparent, and I start to have D written into this first latch. Huh? Are you with me?
Yes, sir.
So now when CK goes to 1, this will become opaque, and this will become transparent.
So it will hold the sample data.
Hai. So now what happens when this becomes transparent? Then whatever was written on over here will come to Q.
Yes, sir.
Hmm?
Okay. So D should be held high until and unless my first part is totally becoming open.
Yes. So this latch is where you may say setup hold are defined.
And so clock to queue delay would totally depend upon the second part of the latch, means sorry, the flip-flop.
Yes, in a stable state. Now, if you really want to test the limits, and that is what we will now look at. If you really want to test the limits, then you will say that, okay, see, if I've sampled, if I've allowed the data in over here, if a change in data is reflected from over here, then I still have the sampling done. Okay. However, if this node is not very stable, if my sorry, if this node, the input of this second tri-state is not stable, then what happens? Then there could be some extra delay between CK to Q.
Okay.
So you define setup and hold times actually based on what is the impact of bringing D closer to the clock edge on the CK to Q delay. We'll just see.
Okay. Yes.
Okay. But is this part clear now?
Yes, sir.
Okay, great. So for the flip-flop, then what we are saying is that for a flip-flop, we have no D2Q timing, and the T pulsar is replaced by T period. So Madhur, you have a question?
Yes, sir. So can we say that this setup time is actually the propagation delay of the first latch?
No. Don't define setup time as propagation delay. Setup time is the minimum duration for which data should be stable before clock edge arrives. That is the definition of setup time. Internally, what it is equal to, okay, there could be many things. There could be delays in clock paths, there could be delays in data paths. So it is not really propagation delay. There is a race condition through which the setup time is defined actually. We will see.
Okay, sir.
Okay. Gagandeep?
Sir, this setup and hold time, they are intrinsic to the flip-flop or a latch. So, sir, is there a way that we can maybe tweak the device parameters and change these hold and setup time?
Yeah. So abhi humne dekha na that, what was Madhur saying? Madhur was saying that it is the propagation delay of the data from the input to the first latch. So if you
Yes.
kind of speed up the input to first latch ka delay, you can reduce the setup time. Why not?
So, do we try doing that always?
Yes. You always want to minimize the setup and hold time.
Okay. So, whatever is the setup and hold time, that is the minimum that designer has tried to achieve.
Yes.
It can't be otherwise.
Yeah. Raghav?
Yes, sir. Sir, I mean the whole time it is occurring because of the, like, I want the time difference when the first transmission gate is completely off and second transmission is completely turning on. So that difference you're calling as the whole time.
Again, hold time is the duration for which data should be held after the clock edge.
Okay.
That is the definition. So don't confuse the definition with all these implementation details. How do I measure the hold time? That was what Madhur was also doing. Madhur was talking about how do I measure the setup time. So he saw, okay, this is the propagation delay. This should be equal to setup time. What I said was there could be some delays on the clock path also. So they need to be reduced. And then that becomes setup time, not just the propagation delays. You're doing the similar assumption that, okay, this delay is now the whole time. No, there is always a clock path also. And that also needs to be considered when you arrive at the value of whole time.
So, but like, for example, the whole time or the setup time, we are defining with respect to the input pin of the flop or the latch, right? So why is my clock path then coming into picture? I mean, I know that from the rising edge of the clock, whenever the rising edge of the clock is, I will have to give that much margin. So if so, like how even my like clock path is coming, I just have to see that.
Yeah, look at the circuit. Look at the circuit. We just analyzed how clock path is important for
Yes, sir.
C to Q delay. Just look at how it is important for setup time and hold time. You will be able to easily reduce this.
Okay. Okay.
Hello?
And so one more thing. So for example, when Devjit asked the question of the propagation delay, you said that there could be some race around condition or there could be variations in the race around condition or that input when I'm getting the latching action happen. So I was not able to get that, sir, actually.
I said there would be some delays on the clock path, so clock and data input are racing amongst each other. What would reach the latch first? You may buffer the clock inside your circuit, no? There was this suggestion. I think you yourself gave the suggestion that we will put a small pulse on the clock and then a latch would behave like a flip-flop. You said that?
No, sir.
Someone said that.
Okay.
So it means that you may want to put some logic on the clock also.
Okay.
And that would mean that clock would also arrive at a different point of time at the latch. Are you able to see this?
Yes, sir. Sir, but like I'm not able to get that. For example, when my clock edge comes, then only I do all these kind of things. Ki from then I see ki how my D is behaving and put constraints on D after my clock edge I have seen. So clock that variation can happen anyway, and clock can arrive any way. But after the clock has arrived,
variation, Jaga, we are not talking about variations yet. We're simply
okay.
talking about what is happening. Variations I will talk about in a little while.
Okay.
But abhi tak we are simply talking about this is the time when clock edge arrives.
Okay.
From the arriving clock edge, I generate an internal clock. That is what I take to those tri-states.
Okay.
So sampling would actually happen when internal clock comes high. Are you able to see this?
Yes, sir. Yes, sir.
So there will be some delay from clock to internal clock. So this delay would mean that there is more margin for sampling.
Yes, sir. Yes.
that needs to be added to the hold time and reduced from the setup time. Therefore, setup time is not simply the propagation delay, and hold time is not simply the propagation delay either.
Yes, yes. I mean that margins have to be added. And
Okay.
so one more thing, sir, with respect to the propagation delays, internal propagation of the clock, I mean because I can see that there is a fixed path, right? That my data will always follow after my input. So can I say that I will have a propagation? I can say that there will be a propagation delay only. There will be, I can come around a stable propagation. There is a one propagation delay because of depending upon the elements, because I am having the inverters in between.
So that propagation delay can also be different for rising and falling edge, na?
Yeah, for rising and falling edge.
How can it be just one propagation delay?
So, yes,
So
sir.
why do you want to arrive at is the definition that setup and hold time are linked to how much the data should be stable before sampling edge or after sampling edge? Is this definition not simple enough?
It's simple. Yes, sir. Okay, sir.
So I'm happy that you're trying to work it out more, but without really doing that analysis on pen and paper yourself, you will simply confuse yourself, Raghav. That is why I said, analyze the circuit, use a pen and a paper, and you will have all the answers with you.
Okay, sir. So actually, I was initially thinking of like, will there be a contamination kind of thing also coming here? Because I couldn't think of that. So that was
There will be contamination delays, yes. Wherever there is a propagation delay like TCQ, there is a contamination delay also there.
So that was
there has to be.
The data were not getting clear because I was not able to see that there could be alternate paths existing, because contamination, I think, when there's only alternate path existing.
Contamination delay could be because of the falling edge. One of the edges is larger or has more delay. The other transition is slower because of either skewing of inverters or whatever reason. Can happen, na?
Okay, sir. So different input slew, for the different input slew, if I'm getting different delays, I can characterize them also like a contamination propagation.
Yeah.
Because earlier you used to think that when the different paths.
If there is a different path, then obviously that different path would lead to a significantly different propagation and contamination delay. But even in the same path, there could be very significant difference between propagation and contamination for the two different edges.
Yes, sir.
So you characterize that.
Okay.
Again, the definition there is longest delay and shortest delay. It never said that it has to be from two different paths. Did it say that?
So that in the combination we did by calculating effective resistance, we used to
That was examples. That was examples. What was the definition of propagation delay and what was the definition of contamination delay?
So the shortest delay is the
exactly. So if that shortest delay is coming for a different edge, then that becomes the contamination delay.
Okay, so if the different slew is also triggering a shortest delay, that can also be a contamination. Okay.
Yes, that is why I'm saying that stick to the definition of setup time as that. Then measurement is a different thing. Every circuit you will have to analyze differently and say, okay, this is my setup time and this is where my hold time is.
Okay.
Okay, that is why I'm saying ki don't violate the definition. The definition is about minimum duration for which data should be stable before clock edge and after clock edge. Before clock edge is setup time, before sampling edge is setup time, after sampling edge is hold time.
Okay, okay, sir. Okay.
Stick with this definition. Now, however complex circuit you may encounter, you can always find out what the setup and hold time is. If you have to merge 2 or 3 delays, you have to simply measure 1 delay, 2 delays. All that is now inconsequential if the definition is clear. You will do the implementation correctly.
Okay, sir.
If you learn only one implementation, then as soon as another implementation comes, you will completely go bonkers. You will get confused.
Okay, okay. So, sir, like for example, in the timing libraries where I have the characterization for the flops, so I have this clock to Q delay characterized. So in that and in that two parameters are the input slew and the load. So, sir, in that table itself, I will be getting, I will be able to see the minimum value. I will say it is contamination, and the maximum value in the LLDM table itself, the propagation thing.
Even for the same clock and same load.
Okay.
The rising transition and falling transition could be different.
Yes, sir. Yeah. So 2 tables.
Yes.
Okay. So in those 2 tables, the minimum value, I will say that this is a contamination thing.
Yes.
Okay. Okay, sir. Now get it, sir. Thank you, sir.
Okay.
Yes.
Madhur?
Sir, in any design process, we first do functional simulation without any timing information. So if I do not have all these timing informations, then where will my data change? I mean, whenever I do some design on Verilog and test it using a test bench, then I see that data almost always changes exactly at the clock edge only, not before that,
Yeah.
not after
Because
that.
so there are there are simulations which you do. So what you're talking about is the logical simulation.
Yes, a functional simulation only.
No. Functional
Pre-sim.
simulations also have delays embedded in them. Notional delays, unit delays. It is referred to as unit delays. You put those delays in terms of unit delays.
Okay. Okay. So
In
yes,
those
sir.
functional
So,
simulations, you will see data will be toggled 1 unit delay before clock edge.
1 unit delay.
A little before clock edge.
Okay, so then that hash 1, hash 0.5, those.
Yes.
So I have to explicitly put it there before, in order to get my functionality correct. Otherwise, I don't even get my functionality correct.
If there
by
are
doing-
delays, if that is how the Verilog has been modeled, yes.
Okay. Okay.
Okay. Yeah. Raghav, you have anything else? Your hand is still raised.
Sir, a small question.
Yeah.
Sir, for the whole time, and basically in the first stage of the flip-flop, basically there is a latch. Let's say the flip-flop is a positive edge triggered, and
Mhm.
the first stage is the negative latch. So, sir, once the whole time has been done for the first latch, if the first latch has held the data at the output of itself, so I can now change the D input. So largely the whole time of complete flip-flop depends upon the whole time of first latch. Is it so?
Yeah. वही मैंने कहा ना, first the setup and hold are largely dependent on the first latch operation. That is how if you want to improve the setup and hold, you improve the delays in the first latch.